Full sharing. Full sharing. Yeah. Today we are discussing about Gram-Schmidt orthonormalization process. Only one theorem, big theorem. Unit 13. Unit 13. Gram-Schmidt. Gram-Schmidt. SCH MIDT. Gram-Schmidt MIDT. SCH. Orthonormalization. Orthonormalization process. Orthonormalization process. 3.1 theorem. Statement. Theorem. Statement. What is it? Let Xn be a. Let Xn be a. Let Xn be a sequence of linear linearly independent vectors. Li is linearly independent vectors. X and inner product of X. IPS. Inner product. IPS. Inner product space X. Inner product space. Then there exists an atom. Then there exists an orthonormal sequence. Orthonormal sequence. Orthonormal sequence by n. Orthonormal sequence of vectors in X. Vectors in X. Vectors in X. Thus that for any natural number, such that for any natural number. ఎవరు సౌండ్ వస్తుంది అదే మ్యూట్ లో పెట్టుకోండి. n linear space. Linear span. SP means linear span. x1, x2, etc. xn. That equal to linear span of linear. SP means span. Linear span of y1, y2, etc. yn. Proof. The proof by induction. Induction means mathematical induction. First put n equal to 1 is true. N equal to induction means induction and complete induction is different. Induction means generally what is our previous knowledge. Put n equal to 2. By induction hypothesis, n equal to k is true. K equal to k plus 1 is true. Here complete mathematical induction means n equal to 2 and n equal to 1 is true. N equal to 2 is true. That is called complete mathematical. We are Now proof by induction, mathematical induction. Let us verify the theorem n equal to 2. Verify. Put n equal to 1. So x1 is not equal to 0 because the linear independent set cannot contain non-zero vectors. Therefore, norm of x1 is not equal to 0. Where norm is on x, where norm is where is the norm? Is the norm on x, on capital X, induced by inner product means in fact norm x equal to, norm x can be written as under root of inner product of x comma x. Put x1 in, put y1 equal to x1 by norm x1, x1 by norm x1, x1 by norm x1. Then clearly norm y1 equal to 1. Norm y1 equal to. And linear span x1 equal to linear span of y1. Linear span, LIN, linear span, SP means linear span of x1, that equal to linear span of y1. So next, consider the linear independent set. Consider the linear independent set. Li means linear independent set. Set x1 comma x2, and let z1 and let z2 equal to x2 minus x2 comma y1, inner product of x2 comma y1 outside y1. Then z2 is not equal to 0. Then z2 is not equal to 0. Otherwise, x2 minus y1 equal to 0. OW means otherwise x2 minus inner product of x2 comma y1, inner product y1 equal to 0. Y1 equal to 0. So that implies x2 equal to, transpose this to x2 equal to inner product of x2 comma y1 into y1. So now substitute y1 value. Here y1 equal to what we wrote? Y1 equal to x1 divided by norm of x1. That value I am substituting here. Inner product of x2 comma y1. Now y1 means what I am substituting from y1 this place. X1 in place of x1 divided by norm of x1. Next page. Norm of x1. That is x2 is a scalar multiple. That means x2 is a scalar multiple of x1. x2, x1 are linearly independent. That means x2 comma x1 are linearly independent. Li means linearly independent. Now put y2 equal to. Now put y2 equal to z2 by norm z2. z2 divided by norm z2. y2 equal to z2 divided by norm z2. Then y1 y2 is an orthonormal set. Then y1 comma y2 orthonormal is an orthonormal set, and linear span of set, and LIN linear SP means linear span of x1 x2 equal to linear span of x1 comma x2 equal to linear span of LIN means linear span and linear SP means linear span of y1 comma y2. So clearly now y1 equal to, here what we are observing, clearly norm of y1 equal to 1, that equal to norm of y2. So inner product of y1 comma y2, that can be written as inner product of y1 as it is. Here from y2 we are substituting this value. What is y2? Z2 divided by norm z2. Norm z2. So inner product that equal to 1 divided by norm z2 as it is. Outside we are taking. Inside what will be there? Inner product of y1 comma z2. Right. So that equal to 1 divided by norm z2 as it is. Inner product of y1 comma x2 minus inner product of x2 comma y1, inner product of y1 from above previous result. This is that equal to 1 by norm z2 as it is. Inner product of y1 comma x2, inner product of minus conjugate of x2 comma y1 into inner product of y1 comma y2 in the set symbol.
Sir, y1 ఉంది sir.
y1
రెండు y1 లే ఉన్నాయి sir.
y1 comma y1 ఇది ఎందుకు అంటే ఇది y1 comma y1 ని ఎట్లా రాస్తామంటే దీన్ని నామ్ ఆఫ్ y1 ని రూట్ లో రాసాం. నామ్ ఎక్స్ కి మనం ఏం రాసుకున్నాం? నామ్ ఎక్స్ ఉన్నప్పుడు అండర్ రూట్ ఆఫ్ ఇన్నర్ ప్రోడక్ట్ ఆఫ్ ఎక్స్ కామా ఎక్స్ రాసామా?
Yes sir.
దాని y1 comma. So that equal to 1 by norm z1 norm z2 within the set symbol norm y1 comma x2 inner product of minus inner product of y1 comma x2 inner product set symbol. Since ఎందుకు రాసామంటే norm of y1 square that equal to inner product of y1 comma y1 that equal to 1 meaning. ఇంకొకటి ఏంటి? norm of the inner product of x2 comma y1 conjugate రాసాం కదా, that is nothing but
y1 comma x2.
y1 comma inner product of y1 comma x2 inner product రాయాలి, లేకపోతే ఆ ప్రాపర్టీ అప్లికబుల్ కాదు.
Okay, sir.
Hence, y1, y2 is an orthonormal set. Hence, y1, comma, y2 is an orthonormal set. Orthonormal set. Next. పెద్ద థీరం ఒకటే ఉంది థీరం, మోస్ట్ ఇంపార్టెంట్. సో ఆర్థోనార్మల్ సెట్ అయిపోయింది. తర్వాత సిన్స్ ఏం తీసుకుంటున్నాం? y1 ఈక్వల్ టు 1 డివైడెడ్ బై norm x1 into x1 and y2 equal to 1 by norm z2 into dot x2 y2 equal to minus inner product of x2 comma y1 whole divided by norm of z2 dot norm of x1 into x1 comma y1 y2 belongs to linear span. Here y1 comma y2 belongs to belongs symbol linear span of x1 comma x2. So hence linear span y1 y2 is, and hence linear span of y1 y2 equal to y1 comma y2 equal to linear span of x1 x2 and linear span of and x2 minus inner product x2 comma y1 outside y1 that equal to z2 minus inner product of z2 minus norm z2 into y2 into y2 so that is x2 equal to, that means x2 equal to inner product of x2 comma y1 into y1 plus norm z2 into y2. So, and hence x1 x2 both belongs to linear span of, hence both x1 comma x2 both belongs to linear span of y1 y2. Linear span of y1 y2. Linear span of y1. That implies linear span of x1 equal to x2. That implies linear span of x1 comma x2 equal to linear span of y1 comma y2. So which proves the theorem is true for n equal to 2. It is true for n equal to 2. So now I assume that corresponding to the sequence vectors have an orthonormal sequence vectors of vectors such that what we need to write. So linear span of orthonormal vectors such that linear span of x1 comma x2 equal to linear span of y1 comma y2. So for y1 comma y2, so x1 here, so on xk, sequence continuation. Here y1 comma y2 so on yk for k equal to 1 2 3 so on, right? Next, now we show that the theorem is true for n. Our aim now construct, so to construct vector yn, to construct vector yn construct vector yn such that y1 comma y2 comma etc yn is an orthonormal set, is an orthonormal set. So linear span of, so linear LIN linear, SP means linear span of x1 comma x2 etc xn, that equal to linear span of y1 comma y2 comma so on yn. So to this end, consider the vector zn equals to xn minus sigma I equal to 1 to n minus 1. So inner product of xn comma yn, into y1. Note this z1 is not equal to 0, meaning not equal to 0. Otherwise xn, which implies to xn, otherwise xn minus sigma I equal to 1 to n minus 1 xn, inner product of xn comma y1, inner product of y1, which would imply xn belongs to linear span of y1 comma y2 comma etc yn minus 1, that equal to linear span of set symbol x1 comma x2 comma etc xn minus 1, which will contradict the vectors, x1 x2 are linearly independent, x1 comma x2 etc xn are li means linearly independent. Put yn equal to zn by norm zn divided by norm zn. Now our claim is the set is not the orthonormally set. Our claim is y1 comma y2 comma etc yn is an orthonormal set, and linear span of y1 comma y2 etc yn, that equal to linear span of x1 comma x2 etc xn. So clearly now yn equal to here norm of yn equal to 1 for all yn equal to 1 for all I equal to 1, 2, etc. Also, so inner product of, that means inner product of yn comma y1, that equal to inner product of zn whole divided by norm zn comma y yi yj inner product, that equal to 1 by norm zn equal to zn comma yj inner product of yj, that equal to 1 by norm of zn is outside
Sir,
inner inner
ఇక్కడ ఇన్నర్ ప్రొడక్ట్ లో yn yi సార్ y1
j
ఇక్కడ సార్ ఇస్ ఈక్వల్ టు యువతల
is equal
LHS సైడ్ సార్
LHS ఇది yn y2 y ఇది ఇదేనా LHS లో అడిగింది yj
yn y1
yj j నాట్ i
ఓకే
ఈ ఆల్రెడీ యూజ్ చేసాం టాప్ లో, ఇక్కడ j వస్తుంది, j కి కండిషన్ వస్తుంది అనమాట,
ఓకే
yi కి yj కి మళ్ళీ 2 స్టెప్స్ నెక్స్ట్ స్టెప్ తర్వాత కండిషన్ రాద్దాం. నామ్ zn xn inner product of xn minus sigma I equal to 1 to n minus 1 inner product of xn comma yj that equal to inner product of yi comma yj, print wrong print padindi yj yi yj that equal to 1 by norm zn that is bracket inner product of xn comma yj inner product minus sigma I equal to 1 to n minus 1 inner product of xn comma xn comma yj into inner product of yi comma yj inner product, so that equal to 1 divided by norm zn inner product of xn comma yj inner product minus inner product xn comma yj. So see here yi comma yj that equal to 1 if I equal to j condition, 0 if I is not equal to j, so note condition that equal to 0 for all j equal to 1 to n minus 1. No, that's enough. No need of that. So this implies that implies y1 comma y2 etc yn is orthonormal set of vectors, is an orthonormal set of x. Next we show that linear span xn equal to linear span. Next we need to prove RTP means required to prove what will linear span of y1 y1 comma y2 etc yn that equal to linear span of x1 comma x2 etc xn by induction hypothesis. Induction hypothesis means given data meaning. Induction hypothesis. Next one. So therefore we have yi belongs to linear span of y1 comma y2 etc. yn minus 1 that equal to linear span of x1 comma x2 etc. xn minus 1 that is subset are equal to linear span of x1 comma x2 etc. xk for all k equal to 1 to n minus 1. So and here yn equal to zn divided by norm zn. That equal to 1 by norm zn. Inner product of xn minus sigma I equal to 1 to n minus 1. Inner product of xn yi comma yi into yi. So inner product belongs to linear span of x1 comma x2 etc. xn. Since xn belongs to linear span of x1 x2 xn and n equal to 1 to n minus 1 xn yi belongs to linear span of n. Hence that are step of solving. Hence linear span of y1 comma y2 etc. yn is subset are equal to linear span of x1 comma x2 etc. xn. So on the other hand xi belongs to linear span of x1 comma x2 etc. xn minus 1 that equal to linear span of y1 comma y2 etc. yn minus 1 These subset are equal to linear span of y1 comma y2 etc. yn. Hence this completes the theorem. So ipudaithe mathematical induction to manam improve chesam. General ga manam previous naadu cheyandi mathematical n equal to 1 is true, n equal to k is true, k equal to k plus 1 is true. Kani ikkada మనం యూజ్ చేసింది ప్రిన్సిపల్ ఆఫ్ కంప్లీట్ మ్యాథమెటికల్ ఇండక్షన్ థియరం. అదేంటి పుట్ n equal to 1, n equal to 2, n equal to k అట్లా ఇచ్చేసింది. నెక్స్ట్ థియరం. నెక్స్ట్ యూనిట్ 14 ఇన్ఈక్వాలిటీస్. యూనిట్ 14 inequalities in Hilbert space. Inequalities in HS. HS means Hilbert space. Rees-Fisher theorem. RASZ. Rees-Fisher theorem.
Sir, Bessel's inequality అవసరం లేదా సార్?
Huh?
Bessel's inequality.
కంపల్సరీ అది లేని రీస్ ఫిషర్ థియరమే రాదు. ఇన్ఈక్వాలిటీస్ ఇన్ హిల్బర్ట్ స్పేస్ రీస్ ఫిషర్ థియరం రావాలంటే బెసెల్స్ ఇన్ఈక్వాలిటీ కంపల్సరీ కావాలి. దాన్ని చేస్తాం మనం ఫస్ట్ ప్రూవ్ చేసేది. 14.3.1 బెసెల్స్ ఇన్ఈక్వాలిటీ. Statement let capital X be an inner product space. IPS means inner product space, and A be an orthonormal subset of X, and capital A be an orthonormal set, orthonormal subset of X, Then for all finite numbers, finite number of vectors, x1 comma x2 etc xn belongs to A for any x belongs to capital X. That means sigma I equal to 1 to n, inner product of x comma x, inner product of x comma x whole square model whole square is less than or equal to norm x whole square. This is Bessel's inequality for finite case. So this inequality holds if and only if x is a linear combination of x1, x2, etc. Proof. Now, let small x belongs to capital X. Put y equal to sigma I equal to 1 to n, inner product of x comma xi, here also x comma xi, outside inner product xi. Then we have the orthonormality of x1 comma etc xn and the property of inner product space, IPS, property of inner product space. So inner product of x comma y, but we let inner product of x comma sigma I equal to 1 to n. ఇదే ఈ y ని ఇక్కడ సబ్స్టిట్యూట్ చేస్తాం. Sigma I equal to 1 to n inner product of x comma xi into xi inner. So that equal to x అని కూడా లోపల తీసుకు ఈ సిగ్మా ని బయటికి తీసుకొస్తాం. Sigma I equal to 1 to n inner product of x లోపల తీసుకుంటాం. x comma inner product of x comma xi inner product of xi outside xi inner product close. Next, that equal to sigma I equal to 1 to n sigma inner product of x comma xi conjugate as the inner product of x comma xi using inner product space. That is nothing but conjugate means here already previously we discussed z is a complex number, so another is z bar. Z into Z bar is nothing but mod Z whole square now from complex. Similarly, here consider this is considered Z bar. This can be written as sigma I equal to 1 to n. 1 to n. That can be written as now mod sigma x comma xi whole square. That equal also. So opposite inner product of y comma x. That can be written as x comma y conjugate, inner product conjugate. That equal to sigma I equal to 1 to n mod x comma inner product of x comma xi whole square conjugate. That equal to sigma I equal to 1 to n mod sigma x comma xi mod whole square. That is nothing but inner product of x comma y. What we proved? Inner product of y comma x equal to inner product of condition. So then inner product of y comma y. That equal to, so inner product of sigma I equal to 1 to n equal to 1 to n. So inner product of x comma xi into xi the comma sigma I equal to 1 to n inner product of x comma xi outside xi inner product bracket. That equal to sigma I equal to 1 to n inner product of x comma xi inner product of x comma xi bar. That is nothing but sigma I equal to 1 to n modulus of sigma x comma xi modulus whole square. That is nothing but inner product of x comma y. So x1 x2 are the orthonormal sets already we discussed. So hence what we do, hence here 0 is less than or equal to norm of x minus y whole square can be written as what we'll write, inner product of x minus y comma x minus y by normality of conditions in inner product. This will write x comma inner product of x comma x minus y minus y comma x minus y inner product. That equal to inner product of x comma x minus inner product of x comma y minus inner product of y comma x plus inner product of y comma y. So that is nothing but inner product of x comma x is in normal condition norm x now whole square minus inner product of x comma y. So that implies sigma I equal to 1 to n. So modulus of x comma xi whole square is inner product of x comma y. That is less than or equal to norm of x square, hence proof. ఇందులో యూజ్ చేసిన ఇన్నర్ ప్రోడక్ట్ ప్రాపర్టీస్ అండ్ నార్మల్ లీనియర్ ప్రాపర్టీస్. నౌ 14.1 ఫిషర్ థీరం. 14.4.1 రీస్-ఫిషర్ థీరం.
సార్ ఆ తీరం అంతవరకే చాలా సార్.
చాలు, ఇంకా కరోలీ వేరియబుల్ ఉన్నది అన్ని అవసరం ఇక్కడ వరకు హెన్స్ ప్రూవ్డ్ అని పెట్టి సార్. నెక్స్ట్ రీస్-ఫిషర్. RIESZ is Fisher theorem. Is Fisher theorem. Statement. Let Xn be a sequence. Let Xn be a sequence. Let Xn be a sequence of orthonormal vectors. Normal vectors. Orthonormal vectors in Hilbert space. HS means Hilbert space. H and alpha n be a sequence in scalars. Alpha n be a sequence of scalars. Sequence of scalars. Then alpha n belongs to L2. Yes, that means sigma n equal to 1 to infinity. Norm alpha mod alpha whole square less than infinity. If and only if there is a vector small x belongs to capital X such that x comma xn belongs to alpha n for all n. So proof. Let alpha n belongs to L2. That is sigma n equal to 1 to n, 1 to infinity. Alpha n whole square less than infinity. So we claim that the series is converges in S. We claim that the series sigma n equal to 1 to n, 1 to infinity, alpha n xn converges. CGS means converges in H, means Hilbert space, meaning to show that it is enough to show that sequence of partial sums. Partial sums. Sigma I equal to 1 to n alpha k xk is Cauchy sequence in Hilbert space. Is Cauchy sequence in H, means H is complete, meaning right. Let epsilon greater than 0 be given since sigma n equal to 1 to infinity, alpha n whole square less than epsilon square for all n is greater than m is greater than or equal to n naught. So therefore n is greater than m is greater than or equal to n naught. We have norm sigma I equal to 1 to n alpha I xi minus sigma I equal to 1 to n alpha I xi norm whole square, that equal to norm sigma I equal to m plus 1 to n alpha I xi norm whole square, that equal to inner product of sigma I equal to n plus 1 to n alpha I xi comma sigma I equal to m plus 1 to n alpha I xi inner product. that equal to double sigma. Sigma I equal to m plus 1 to n, and sigma j equal to m plus 1 to n. That means alpha I into alpha I conjugate, alpha I, alpha j conjugate, inner product of xi comma xj, that equal to sigma I equal to m plus 1 to n, m plus 1 to n, alpha I conjugate, inner product of x I comma x I, that equal to sigma I equal to m plus 1 to n, that means modulus of x alpha n whole square less than epsilon square. So here xn is the orthonormal sequence. Hence what we got? Hence we got, that implies norm of x I equal to 1 to n, 1 to n, alpha I xi normal less than epsilon, less than, for all n is greater than, m is greater than or equal to n naught, n naught. So since the sequence is a Cauchy in H, Hilbert space is series. So that implies series Hilbert space. That series converges. That series converges. CGS may converges in H. Then x equal to, we can write sigma n equal to 1 to infinity alpha n xn, that equal to limit n tends to infinity sigma I equal to 1 to n alpha I xi belongs to capital H. Next. So as inner product space is jointly continuous function, IPS means inner product is jointly continuous. CTS means continuous function. For each m we have, inner product of x comma xm, that equal to inner product of limit n tends to infinity, sigma I equal to 1 to n alpha I xi comma xm inner product, that equal to limit we are taking outside, limit n tends to infinity outside, in sigma I equal to 1 to n alpha I outside, inner product of xi comma xm, that equal to alpha m. So inner product of, here this meaning inner product of xi, inner product of xi comma xm is nothing but 1. So I equal to m, n is greater than or equal to m, n is greater than a conditional alpha. So sigma I equal to 1 to n alpha I inner product of xi comma xm equal to alpha m. So conversely, suppose that there is this small x belongs to capital X, such that inner product of x comma xn equal to alpha n for all n. So then by Bessel's inequality, then by Bessel's inequality, Then by Bessel's inequality, we have sigma n equal to 1 to infinity modulus of alpha n whole square, that equal to sigma n equal to 1 to infinity modulus of inner product x comma xn mod whole square is less than or equal to norm x whole square is less than infinity. Ide Bessel's inequality. So this completes the proof. That means alpha n, sequence alpha n belongs to L2. This completes the proof. Hence proof. అయిపోయింది. ఆ థిరంలో ఏం నేర్చుకున్నాం ఇప్పుడు? బెసెల్స్ ఇన్ఈక్వాలిటీ, ఫిషర్, రీస్ ఫిషర్ థీరం, నెక్స్ట్ గ్రామ్ ష్మిట్ ఆర్థో నార్మల్ ప్రాసెస్. ఈ మూడిట్లో ఒక క్వశ్చన్ పడిపోయింది 20 మార్క్స్.
ఓకే సార్.
థ్యాంక్ యూ. We'll meet tomorrow 4:30.
Thank you, sir.
Welcome.